December 4th, 1908. Chicago Industrial Exhibition. 10,000 spectators packed around two machines that would settle the most important engineering debate in American manufacturing history. European precision versus American power. Continental engineering wisdom declared it impossible. Heavy steel cutting destroys accuracy. Light cuts preserve precision. No compromise existed between speed and quality. But two Massachusetts farm boys had spent 20 years in Cleveland proving European experts wrong. Worcester Reed Warner and Ambrose Swasey built turret lathes that channeled cutting forces instead of fighting them, massive cast iron bases, solid steel spindles, rigid tool holders that transmitted vibration directly to bedrock-stable foundations. While European machines crawled through steel with delicate cuts, American lathes devoured metal aggressively and held tolerances European craftsmen thought impossible. The demonstration was supposed to prove European methods superior. Instead, it would reveal engineering principles so revolutionary that machines built on those foundations 60 years later still outcut modern equipment that shakes apart under loads those old Cleveland lathes handled effortlessly. Two different philosophies of metal cutting were about to collide. Only one would survive. In 1880, precision machining belonged to Europe. Swiss craftsmen had perfected techniques for cutting delicate watch components, their lathes capable of holding tolerances measured in fractions of thousandths. German engineers had developed mathematical approaches to tool geometry that produced surfaces smooth enough for bearing races in the finest mechanical instruments. British manufacturers had built their reputation on machines that lasted decades, their cast iron beds seasoned for years before final machining to eliminate internal stresses that could compromise accuracy over time. The established wisdom crossed the Atlantic with every European-trained engineer who set foot in American factories. Heavy cutting destroyed precision. This was fundamental physics, not opinion. To machine steel properly, you fed the cutting tool slowly through the work, removing metal in light passes that generated minimal heat and vibration. You accepted that precision work took time, that aggressive cutting produced rough surfaces, that speed and accuracy existed in permanent opposition to each other. At Pratt & Whitney's Hartford facility, two machinists had spent years watching this European orthodoxy play out in American manufacturing. Worcester Reed Warner, 34 years old, possessed the methodical patience of the Massachusetts farm boy he had been before discovering his obsession with astronomical precision. He spent evenings bent over telescopes he had built himself, tracking celestial movements with the same meticulous attention he brought to measuring machine tool performance during the day. His notebooks contained detailed observations of how cutting forces propagated through different machine structures, diagrams that traced vibration patterns the way he mapped stellar coordinates across night skies. Ambrose Swasey, also 34, had grown up among the mills and machine shops of New Hampshire, where his father had taught him that understanding machinery meant feeling it through your hands before trusting what instruments told you. He could detect the subtle vibrations that preceded tool failure minutes before other machinists heard anything unusual. When European-trained supervisors explained why their careful, conservative cutting methods produced superior results, Swasey would nod respectfully while privately questioning why machines needed to fight the metal instead of working with it. Both men had spent their careers watching European-educated engineers design machines that crawled through steel. The standard approach called for removing metal in passes measured in hundredths of an inch, with cutting speeds so conservative that a single component might require hours to complete. Tool changes interrupted work constantly as cutting edges dulled under the careful, persistent pressure that European theory demanded. The machines themselves vibrated continuously, not violently enough to destroy the work, but enough to remind everyone that metal cutting remained a battle between tool and material. When bicycle manufacturing exploded across America in 1881, everything changed overnight. Suddenly, factories needed to produce thousands of identical steel components, handlebar stems, sprockets, axle housings, brake levers. The recreational bicycle craze had created demand that no one had anticipated. European methods couldn't possibly meet the production requirements. A Swiss precision lathe operated according to continental best practices might spend 2 hours machining a single bicycle sprocket to specification. American manufacturers were receiving orders for hundreds of sprockets per day, with delivery schedules that assumed 20 finished parts per hour. Warner and Swasey found themselves studying the fundamental problem from their workbenches at Pratt & Whitney. European machines fought the metal. Their designs assumed that cutting forces were enemies to be minimized and controlled. But what if those forces could be channeled instead of resisted? What if the energy of aggressive cutting could be directed through machine structures specifically designed to absorb and transfer that energy without generating the vibrations that destroyed precision? The concept violated everything their European-trained supervisors had taught them. Heavier cuts generated more heat, which caused dimensional changes in both cutting tools and workpieces. Aggressive material removal created dynamic forces that no machine structure could completely eliminate. Higher cutting speeds reduced tool life exponentially, making production economics unworkable. These weren't opinions, they were established engineering principles backed by decades of continental manufacturing experience. But Warner's background in astronomical instrument making had taught him that rigid mounting eliminated vibration more effectively than damping systems. Swasey's intuitive understanding of metal behavior suggested that cutting forces, properly channeled, could actually stabilize a machine rather than destabilize it. Together, they began sketching designs for turret lathes that would embrace aggressive cutting rather than avoid it. The breakthrough required abandoning conventional lathe architecture entirely. European machines used bed plates, essentially flat cast iron surfaces that supported the working components. Warner and Swasey envisioned monolithic bases that would absorb cutting forces and transfer them directly to the foundation. Instead of hollow spindles designed to minimize weight, they imagined solid steel shafts that would transmit forces without deflection. Rather than lightweight turrets that indexed quickly between cutting positions, they conceived turrets that clamped rigidly to the machine structure during cutting operations. By winter of 1881, they had made their decision. Pooling their combined savings of $6,000, every cent either man possessed, they prepared to leave Hartford for Cleveland. The Ohio City offered advantages that Connecticut couldn't match. Steel mills provided endless supplies of raw material, and a workforce accustomed to heavy manufacturing understood that building revolutionary machines required different approaches than maintaining existing ones. The morning they submitted their resignations to Pratt & Whitney, Warner carried detailed drawings for their first turret lathe design. Swasey had already identified a Cleveland machine shop willing to undertake the complex castings their design demanded. Neither man had any illusions about the challenge they faced. American machine builders had attempted to overcome European engineering superiority before. Most had failed within months, their aggressive American optimism crashing against the mathematical realities that European education had spent centuries refining. But Warner and Swasey believed they had identified the fundamental flaw in European thinking. Continental engineers designed machines to minimize cutting forces. Americans could design machines to maximize the productive use of those same forces. Cleveland's industrial district in 1882 offered exactly what Warner and Swasey needed: foundries capable of pouring massive castings and machine shops equipped to handle the precision work their revolutionary design demanded. The partners rented a cramped workshop on the east side of the city, close enough to the steel mills that the constant hammering of trip hammers and the hiss of steam-powered machinery provided a soundtrack to their 18-hour workdays. Their first decision violated every principle of conventional lathe construction. European manufacturers built machines by assembling components, bed plates, headstocks, tailstocks, and tool holders, then addressed vibration problems as they emerged during testing. Warner and Swasey reversed the entire process. They started with the vibration solution and built everything else around it. The foundation represented their most radical departure from established practice. European lathes used bed plates that typically weighed between 800 and 1,200 pounds, substantial castings that provided adequate rigidity for conservative cutting operations. Warner and Swasey specified a monolithic base weighing 8,000 pounds. The casting alone cost more than most complete European machines. but Swasey had calculated that mass alone wouldn't solve their vibration problem. The internal structure mattered more than total weight. Working with Cleveland Iron Works, they developed a specially formulated iron alloy that contained higher percentages of carbon and silicon than standard gray iron. The chemistry produced a material that absorbed vibrational energy rather than transmitting it through the structure. More critically, they designed internal ribbing patterns that divided the massive casting into interconnected cells, each rib positioned exactly 6 inches from its neighbors. When cutting forces generated vibrations anywhere in the structure, the energy dissipated through this internal network instead of propagating to the cutting tool. The foundry work required 3 attempts before they achieved acceptable results. The first casting developed internal voids when molten iron cooled unevenly through the complex rib structure. The second attempt produced a sound casting, but dimensional distortion during cooling made final machining impossible. Only the third casting, poured with carefully controlled cooling rates and stress relief procedures, met their specifications. Spindle design presented equally challenging problems. European lathes used hollow spindles that reduced rotational inertia and simplified tool-changing operations. The hollow design also reduced weight, which European engineers considered advantageous for precision work. Warner had calculated that hollow construction created the exact weakness their aggressive cutting approach couldn't tolerate. Under heavy loads, hollow spindles deflected microscopically, deflection that destroyed precision even when cutting forces remained within acceptable limits. Their solution required solid steel spindles machined from 3-inch diameter bar stock. The material specification called for chrome molybdenum steel case, hardened to 50 Rockwell hardness, harder than most cutting tools. The spindle manufacturing process took 6 weeks per unit. Each spindle required rough machining, stress relief heat treatment, finish machining to tolerances measured in 0.010 of an inch, final hardening, and tempering operations that brought the finished component to precise hardness specifications. The bearing system that supported these massive spindles demanded equal precision. European machines typically used bronze bushings that required frequent adjustment as wear occurred. Warner and Swasey developed bearing assemblies that used bronze sleeves mechanically locked to the spindle housing. When cutting forces attempted to deflect the spindle, the entire bearing assembly transferred those forces directly to the 8,000-pound base. The spindle, bearings, and foundation functioned as a single rigid system. Their turret innovation became the signature feature that distinguished Warner and Swasey machines from all competitors. European turret lathes used lightweight indexing heads that rotated quickly between cutting positions, an advantage when machining operations required frequent tool changes. But lightweight construction meant these turrets flexed under cutting loads, introducing precisely the vibrations that Warner and Swasey had designed their entire machine to eliminate. Their turret solution used cast iron sections that weighed 400 pounds each. During cutting operations, mechanical clamps locked the turret rigidly to the machine bed. The turret became an extension of the foundation structure rather than a separate component mounted on the machine. Tool holders attached to this turret transmitted cutting forces through the cast iron sections, through the clamping system, directly to the 8,000-pound base. The clamping mechanism itself required 12 patents before they achieved satisfactory operation. The system needed to secure the turret absolutely rigid during cutting, then release instantly for indexing to the next tool position. The final design used wedge action clamps actuated by a single lever. Engagement force exceeded 10 tons per square inch of contact area, sufficient to prevent any movement under the heaviest cutting loads they anticipated. First tests of their completed No. 2 lathe exceeded every prediction they had made. The machine rough-turned a 3-inch diameter steel shaft, removing a 1/4 inch of material per pass in 4 minutes total cycle time. European machines performing identical work required 40 to 60 minutes and produced surfaces that needed secondary finishing operations. The Warner and Swasey machine produced bearing-quality surface finish directly from the roughing operation. More significantly, precision measurements confirmed that aggressive cutting actually improved rather than degraded dimensional accuracy. The rigid machine structure prevented deflection that had plagued European designs. Heavy cutting loads compressed the entire machine foundation system into even greater rigidity. Tool wear decreased because cutting tools operated under steady conditions rather than the constant vibration that dulled European tools prematurely. By 1886, bicycle manufacturers throughout Ohio and Pennsylvania had placed orders for Warner and Swasey turret lathes. Production managers reported cycle time reductions of 60 to 70% compared to European equipment, while tool life improved by comparable margins. Quality control inspections revealed dimensional consistency that European precision machines couldn't match, even operating under ideal laboratory conditions. The breakthrough had required abandoning every established principle of machine tool design, but the results validated Warner and Swasey's fundamental insight. European methods fought cutting forces. American engineering could harness those same forces to achieve both speed and precision simultaneously. By 1890, Warner and Swasey turret lathes had captured 70% of American bicycle manufacturing, but success brought new challenges that threatened to expose the limitations of even their revolutionary design. The explosive growth of automobile manufacturing demanded machining operations that made bicycle production look simple by comparison. Where bicycle components required removing fractions of an inch from relatively soft steels, automobile parts demanded aggressive cutting through hardened forgings with tolerances measured in thousandths rather than hundredths of an inch. The transformation began when Henry Ford's production engineers arrived at the Cleveland factory in October 1903, carrying specifications that seemed designed to test the absolute limits of metal cutting technology. Ford's Highland Park plant needed crankshaft journals machined from solid steel billets, not the pre-formed blanks that other manufacturers used, but raw steel bars that required removing 2 full inches of material to reach final dimensions. The tolerances Ford demanded would have challenged Swiss watchmakers. 0.002 of an inch total variation across surfaces that needed to function as bearing races in engines producing unprecedented power outputs. Charles Morrison, Ford's chief production engineer, spread the drawings across Warner's desk with the matter-of-fact precision of a man accustomed to demanding the impossible. Each crankshaft required 8 journal surfaces, each journal precisely 1 7/8 inches in diameter, with surface finishes smooth enough to support direct bearing contact without secondary grinding operations. The production schedule called for 40 crankshafts per day from a single machine, cycle times that would require completing each journal in 12 minutes or less. European automotive consultants who had examined Ford's specifications declared the requirements mechanically impossible. Hermann Kruger, representing German machine tool manufacturers, had published detailed calculations in Engineering magazine proving that heavy cuts inevitably produced rough surfaces. The mathematics were indisputable. Aggressive material removal generated heat that caused dimensional instability, cutting forces that induced vibrations, and tool wear patterns that destroyed surface quality within minutes of starting any cut deeper than 1/10 of an inch. Warner studied Ford's drawings while Swasey ran preliminary calculations on cutting speeds and material removal rates. The numbers confirmed European skepticism. Removing 2 inches of hardened steel in 12 minutes required feed rates and cutting depths that no existing machine tool could sustain. Even their heaviest No. 4 lathe, designed for the most aggressive bicycle component work, operated at feed rates measured in hundredths of inches per minute. Ford's specifications demanded half-inch per minute feeds with cutting depths approaching quarter-inch per pass. The solution emerged from Swasey's experience building astronomical telescopes during evening hours when the machine shop fell quiet. Large telescope mirrors required mounting systems that eliminated vibration completely, not merely dampened it, but prevented its generation entirely. Traditional telescope mounts use springs and damping materials to isolate optical elements from external disturbances. Swasey had discovered that rigid mounting, properly engineered, performed better than any damping system ever could. The principle applied directly to machine tool design, but required abandoning another fundamental assumption of European engineering. Continental tool holder design emphasized vibration, absorption, flexible mounting systems that allowed cutting tools to float slightly under varying cutting loads. The theory suggested that rigid tool mounting would transmit cutting forces directly to machine structures, generating the precise vibrations that flexible mounting was designed to prevent. Swasey's insight reversed this logic completely. Instead of tool holders that absorbed cutting forces, he designed mounting systems that transmitted those forces directly through the machine structure to the 8,000-pound foundation. The cutting tool became a mechanical extension of the machine base itself. Vibration had nowhere to propagate because the entire system, tool, holder, turret, and foundation functioned as a single rigid mass. The engineering challenge required redesigning their entire tool holding system. European quick-change tool holders used spring-loaded mechanisms that allowed rapid tool changes but introduced flexibility at the precise point where rigidity mattered most. Swasey developed tool holders that clamped directly to the cast iron turret with mechanical force exceeding 15 tons per square inch. Tool changes required several minutes rather than seconds, but cutting performance improved dramatically. The first test took place on December 4, 1904, using a prototype No. 4 lathe equipped with Swasey's rigid tooling system. Ford engineers traveled to Cleveland to witness the demonstration personally, bringing sample crankshaft blanks and precision measuring equipment to verify results independently. The specifications remained unchanged. Remove 2 inches of steel, hold tolerances to 0.02 of an inch, achieve bearing quality surface finish without secondary operations. Warner positioned the steel billet in the lathe chuck while Swasey adjusted cutting tool geometry for maximum material removal rates. The cutting tool itself, a carbide-tipped steel bar measuring 1 inch square, clamped into the turret assembly with mechanical rigidity that made tool and machine indistinguishable. When Swasey engaged the automatic feed, the lathe began removing steel in continuous spirals at rates that defied every principle of conservative European machining. Feed rate, ½ inch per minute, exactly as Ford's specifications demanded. Depth of cut, ¼ inch per pass, deeper than most European machines attempted in 10 passes. The steel came away in long, continuous chips that indicated optimal cutting conditions, no chatter, no vibration, no tool deflection. Most remarkably, the surface finish appeared smooth enough for bearing applications before any measuring instruments confirmed dimensional accuracy. Morrison timed each operation with a stopwatch, while Ford's quality inspector measured finished surfaces with precision micrometers. Total cycle time per journal, 11 minutes and 40 seconds. Dimensional accuracy, within 1,000th of an inch across all measurements. Surface finish, smoother than European machines produced using their most conservative cutting parameters and requiring 43 minutes per journal. The demonstration convinced Ford's engineers immediately, but the implications extended far beyond automobile manufacturing. Warner and Swasey had proven that American engineering could transform the fundamental relationship between cutting speed and precision. European methods would never recover from this obsolescence. Success bred imitation faster than Warner and Swasey had anticipated. By 1905, machine tool manufacturers from Cincinnati to Detroit were advertising heavy-duty turret lathes that promised to combine European precision with American productivity. Cincinnati Milling Machine Company claimed their new Model 12 could outcut any Cleveland machine while maintaining Swiss-quality surface finishes. Detroit Machine Tool Works published specifications showing cycle times 20% faster than Warner and Swasey's best performance figures. Even smaller manufacturers in Buffalo, Pittsburgh, and Milwaukee were producing machines with massive cast iron bases and rigid spindle systems that closely resembled Cleveland engineering principles. Most concerning was the arrival of Alfred Herbert Limited, Britain's most prestigious machine tool manufacturer, which opened a substantial American factory in Coventry, Connecticut in September 1905. Herbert's reputation rested on 4 decades of building precision machines for British armament manufacturers, lathes capable of machining artillery components to tolerances measured in 0.010ths of an inch. Their American operation promised to combine traditional European precision with American production speeds, directly challenging the fundamental premise of Warner and Swasey's success. Herbert's chief engineer, Dr. Wilhelm Steinberg, had earned his doctorate from Munich Technical Institute and spent 15 years developing advanced machining theory at Krupp's Essen Works. Steinberg understood metallurgy, thermodynamics, and vibration analysis with mathematical precision that American shop-trained engineers couldn't match. His published papers in European technical journals had established theoretical frameworks for predicting tool life, surface finish quality, and dimensional accuracy under varying cutting conditions. When Steinberg examined Warner and Swasey machines in operation at Ford's Highland Park plant, during winter 1906, he identified what he considered fundamental flaws in American engineering approach. Aggressive cutting generated excessive heat that caused thermal expansion in both cutting tools and workpieces. Heavy material removal rates created dynamic loads that stressed machine components beyond their design limits. Most critically, the rigid mounting systems that Americans celebrated actually transmitted destructive forces through machine structures rather than isolating cutting operations from external disturbances. Steinberg's analysis appeared in American Machinist magazine in March 1907 under the title Theoretical Limitations of Aggressive Machining Methods. The article presented mathematical calculations proving that American techniques achieved temporary speed advantages by sacrificing long-term accuracy and machine life. European methods, while slower, produced superior results because they recognized fundamental physical laws that aggressive cutting violated. The article concluded with a direct challenge. Herbert Limited would demonstrate their newest precision turret lathe against any American machine under identical cutting conditions. The test would machine identical steel forgings using identical cutting tools, with precision, surface finish, and cycle time measured independently and published in American Machinist. The demonstration would settle the engineering debate with empirical evidence rather than theoretical arguments. Warner accepted immediately, recognizing that refusing Steinberg's challenge would validate European claims about American machining limitations. The demonstration was scheduled for December 4, 1908, at the Chicago Industrial Exhibition, the largest gathering of manufacturing engineers in North America. American Machinist magazine agreed to publish complete test results, including precision measurements, surface finish analysis, and detailed cycle time documentation. 10,000 spectators packed the exhibition hall on demonstration day, including representatives from every major machine tool manufacturer in America and Europe. The test specifications required machining identical steel forgings, chrome molybdenum alloy components weighing 40 pounds each with final dimensions demanding tolerances within 1/1000th of an inch across all surfaces. Both machines would remove approximately 15 pounds of material per forging, simulating the heavy cutting conditions that had made Warner and Swasey machines famous. Herbert's machine performed first, operating with the methodical precision that characterized European engineering philosophy. Cutting speeds remained conservative, feed rates stayed within established parameters, and material removal proceeded in carefully controlled passes. The surface finish appeared flawless under inspection. Dimensional measurements satisfied all tolerance requirements, and total cycle time, 38 minutes per forging, represented respectable productivity by European standards. Warner and Swasey's No. 4 lathe began its demonstration with characteristic aggressive cutting parameters. Feed rates doubled Herbert's performance immediately. Cutting depths exceeded European practice by substantial margins, and material removal rates demonstrated the spectacular productivity that had captured American automobile manufacturing. For 37 minutes, everything proceeded exactly as Warner and Swasey had predicted. Then catastrophe struck with sudden, unmistakable violence. The steel forging began vibrating in the chuck with amplitude that grew rapidly from barely perceptible tremor to violent oscillation that shook the entire machine foundation. The cutting tool, unable to maintain contact with metal surfaces moving unpredictably, shattered against the spinning workpiece in a shower of carbide fragments. Automatic safety systems stopped the spindle immediately, but damage was complete and visible to every spectator in the hall. European engineers in the crowd exchanged knowing glances while American observers stood silent, stunned by the public failure of methods they had assumed were proven beyond question. Steinberg approached the disabled machine with professional courtesy, examining the broken components, while Warner and Swasey investigated the cause of vibrations that should have been impossible given their machine's design. The investigation required dismantling portions of the 8,000-pound base to examine internal structure. What they discovered validated Steinberg's theoretical predictions in the most damaging way possible. A contaminated batch of molding sand used during the casting process had created internal voids throughout the foundation, precisely the structural weaknesses that their design was supposed to eliminate. Under extreme cutting loads, the compromised foundation had flexed microscopically, introducing vibrations that propagated through the entire machine. Structure. The failure made international headlines within 48 hours. Engineering magazines across Europe published detailed accounts under titles like American Speed Meets European Reality and The Limits of Aggressive Machining Methods. Trade journals that had praised Warner and Swasey innovations now questioned whether American engineering had sacrificed fundamental soundness for temporary competitive advantages. Orders canceled immediately. Ford's Highland Park plant suspended delivery schedules pending investigation of existing machines. General Electric demanded inspection of every Warner and Swasey lathe in their facilities. By January 1909, the company that had revolutionized American machining faced bankruptcy proceedings and the complete collapse of their reputation. The 1908 failure had destroyed Warner and Swasey's reputation, but it had also revealed the exact weakness they needed to eliminate. The problem wasn't their engineering theory. Cutting forces could indeed be channeled through rigid structures to achieve both speed and precision simultaneously. The problem was guaranteeing the internal integrity of massive castings without inspection technology that didn't exist. X-ray examination wouldn't be developed for industrial applications for another decade, leaving foundries dependent on visual inspection and hoping that internal voids wouldn't compromise structural integrity under extreme loads. Warner spent the winter of 1909 developing a solution that abandoned the pursuit of perfect castings entirely. Instead of trying to eliminate internal flaws, he would design around their inevitable existence. The breakthrough came from studying bridge construction techniques, where engineers had learned to build massive structures from multiple components that shared loads through precisely machined mechanical connections. Sectional construction violated another fundamental assumption of machine tool design. European engineers insisted that machine bases required monolithic structures to prevent joints from introducing flexibility that would compromise precision. Any mechanical connection, regardless of how tightly engineered, would flex microscopically under cutting loads. These microscopic movements, amplified through machine structures, would generate the precise vibrations that rigid design was supposed to eliminate. But Warner's calculations suggested that properly designed joints could actually enhance vibration control rather than compromise it. If individual sections were bolted together through machined interfaces with sufficient clamping force, the joints themselves would become part of the energy absorption system. Cutting forces would distribute across multiple sections instead of concentrating in single castings, while any internal flaws would remain isolated within individual components. The engineering challenge required developing entirely new approaches to machine tool assembly. Each section of the new base design weighed between 1,500 and 2,000 pounds, manageable casting sizes that foundries could produce reliably without the internal voids that had plagued their monolithic design. The sections connected through machined interfaces with dimensional tolerances measured in 10,000ths of an inch, creating metal-to-metal contact across hundreds of square inches of bearing surface. The bolting system used grade 8 steel bolts tensioned to 80% of their ultimate strength, clamping forces that exceeded 15 tons per bolt. Warner calculated that 60 bolts per major joint would distribute load sufficiently to prevent any movement between sections under the heaviest cutting operations they could envision. More critically, if any section developed structural problems, only that component required replacement rather than scrapping an entire 8,000-pound casting. Swasey's contribution focused on making the sectional joints contribute to vibration control rather than merely avoiding interference with it. He developed gasket materials, thin bronze sheets with precisely controlled thickness, that filled microscopic irregularities between machined surfaces. Under clamping loads, these gaskets deformed to create perfect metal-to-metal contact, while adding damping characteristics that actually improved vibration suppression compared to monolithic construction. By autumn 1911, their first number 4A lathe, the A designation indicating advanced sectional base design, was completing final testing in Cleveland. Initial results exceeded every prediction they had made. The machine maintained dimensional accuracy under cutting loads that had destroyed their original monolithic design, while sectional construction allowed field repairs that monolithic machines couldn't match. More importantly, the sectional design had solved problems they hadn't anticipated. Transportation became feasible for the first time. Sections could be shipped separately and assembled at customer facilities, eliminating the specialized railroad equipment that monolithic bases had required. Installation simplified dramatically because individual sections could be positioned and aligned using conventional millwright equipment rather than specialized heavy lifting machinery. Warner issued invitations to European competitors in January 1912, proposing a rematch that would settle the engineering debate definitively. This time, the demonstration would take place at Warner and Swasey's Cleveland facility, using their most challenging production work rather than artificial test conditions. European manufacturers could bring their finest machines and most skilled operators. American Machinist magazine would again publish complete results, but the test would continue for 30 days rather than single demonstration sessions. Dr. Steinberg accepted immediately, arriving in Cleveland with Herbert Limited's newest precision turret lathe and 2 master machinists trained at British Armament Works. Representatives from German, Swiss, and French manufacturers brought their most advanced equipment, confident that American methods had reached their practical limits. The 30-day trial began March 4, 1912, with work that would have been impossible using European methods. The number 4. A began machining hardened steel forgings for locomotive driving wheels, components that required removing 3/4 of an inch material depth, while holding tolerances to 1/1000th of an inch across, bearing surfaces 6 inches in diameter. Cycle times that European machines couldn't achieve became routine production rates. European observers documented every aspect of American operations, searching for evidence that aggressive cutting sacrificed long-term accuracy or machine life. Instead, precision measurements revealed dimensional consistency that improved rather than degraded over extended production runs. The sectional base design actually became more rigid under cutting loads as joint interfaces settled into perfect mechanical contact. More dramatically, surface finishes surpassed European results, while cycle times decreased by 60% compared to continental best practices. Tool life improved because cutting tools operated under steady conditions rather than the constant vibration that plagued European machines. By the trial's end, European engineers were requesting detailed drawings of sectional construction principles they had dismissed as impossible 2 years earlier. Ford Motor Company placed orders for 200 Warner and Swasey turret lathes in November 1914. General Electric followed with contracts for 150 machines in January 1915. By the time America entered World War I in April 1917, Warner and Swasey machines had become the backbone of American heavy manufacturing. Wartime production demands validated every principle Warner and Swasey had developed. Artillery shell production required machining operations that combined precision with productivity under impossible deadlines. Aircraft engine components demanded dimensional accuracy that European craftsmen couldn't achieve using traditional methods. Tank armor required material removal rates that no continental machine could sustain. By 1918, the Cleveland factory employed 3,000 workers and produced 60% of America's heavy turret lathes. The machines that European engineers had declared impossible were now machining the weapons that would decide the war's outcome. When Worcester Warner died in January 1920, he knew that American innovation had permanently transformed manufacturing. The engineering principles he and Swasey had developed would continue removing steel aggressively and precisely for the next 50 years, proving that determination and sound engineering could overcome any established wisdom.